Okay, so we looked at a titration in which we had a weak acid with a strong base as the titrant, but of course we could have the opposite as well. We could have a strong acid that we are titrating against a weak base. And so the weak base would be our analyte again, the strong acid would be our titrant. Because if we have a choice, we're going to choose something strong. So the weak base would be the analyte, the strong acid would be the titrant. So an example here would be hydrochloric acid with ammonia. If we do that, what we're going to create there is going to be ammonium chloride as our product. And then you can probably guess that we have to concern ourselves with the hydrolysis of the ammonium at that point. And so our net ionic equation, the chlorine would just go away, right? It's going to be a spectator ion. So again, it doesn't matter what the strong acid is. It could be hydrochloric acid, hydrobromic acid, pick your favorite strong acid. We're really going to have hydronium ion reacting with ammonia to create ammonium. And so whatever our other ion is not going to undergo hydrolysis, and so we won't have to worry about the hydrolysis of that conjugate of our strong acid. At the equivalence point, we would have exactly the same number of moles of hydrochloric acid and ammonia. That would be the definition of the equivalence point. And the second reaction that we need to concern ourselves with is, again, the hydrolysis of that ammonium. When ammonium undergoes hydrolysis, it's going to be a reaction with water to give us ammonia and hydronium ion. So hopefully you can guess at this point. At the equivalence point, we're going to have some extra hydronium ion floating around, which means we're going to have an acidic solution. And so we're going to have, assuming we're at 25 degrees Celsius, we'd have a pH under 7 because we'd have that extra H plus floating around. Our curve looks an awful lot like the weak acid strong base titration. It's just kind of a mirror image of it almost. So we're going to start at a basic solution. It's not going to be super basic, right? Because we have a weak base, so somewhere around 11, let's say, instead of 13 like we would have for a strong base. We're going to fall as we add our acid, our pH will fall until we reach this region where we're going to have both ammonia and ammonium in solution. And hopefully you can guess at this point that that is going to be our buffer region for this. Our equivalence point is going to be at that steepest point of the curve here. And then, of course, we're going to approach that really low pH that we have from the titrant itself. So we start at the pH of the analyte. We've got a buffer region where both our conjugates are present. Our equivalence point is going to be less than 7, so we're going to be slightly acidic. And then we approach the pH of the titrant as we go further and further along. Okay, so at the very start, again, the pH is just going to be the pH of the analyte. So in terms of a process here, it's just a weak base equilibrium problem, right? That's all we have in the solution is just weak base. And so you're going to use your Kb to determine what your hydroxide ion concentration is, do that equilibrium, that can tell you your pH. When we're in the second part of the plot, we are going to have a conjugate acid-base pair, right? So we're going to have a buffer. So notice you're going to assume that forward direction takes place all the way. So in this case, that would be whatever your weak base is reacting with the H plus from the strong acid. Figure out how much excess of that weak base you have, and you'll have moles of weak base there. You'll know how much moles of the conjugate acid have been produced. You know your total volume, add your volumes together. And then you can figure out the concentrations of those two things. So the concentration of the conjugate acid and the conjugate base in the pair. And for the second step, just go back to Henderson-Hasselbalch. I will remind you, Henderson-Hasselbalch has a pKa in it, not a pKb. So you want the pKa of the conjugate acid of this acid-base pair, and you're going to put the conjugate base concentration on top over the conjugate acid. This part does not change just because you're doing it with a weak base instead of a weak acid. The Henderson-Hasselbalch equation stays the same no matter which way you formed this buffer. So you're going to use the Henderson-Hasselbalch to figure out your pH, and it's pretty straightforward. So that Ka is going to come from the conjugate acid. Okay, so at the next point, we're going to look at what do you do when you get to the equivalence point. So if you're at the equivalence point, what that means is you have enough acid so that the number of moles of acid is going to be completely reacted with the number of moles of weak base. So you have the same number of moles of each, essentially. And so what we would do to figure out that we're at the equivalence point is we do the same thing we do for every other step. You start with that first step, you assume the forward reaction happens completely, and what we would see is that we have the same number of moles of acid and base. So we have a complete reaction, we go, okay, we're at the equivalence point. If you're at the equivalence point, you're not going to have any of that weak base or that strong acid left over. All you're going to have left in the solution is the conjugate acid of your weak base. And so you'll figure out how many moles of conjugate acid of weak base you have. You know your total volume, and so you can figure out the concentration of that conjugate acid that you've produced from that first reaction. And so from there, now you consider the hydrolysis of that conjugate acid. Well, it's just going to be an acid dissociation reaction, right? And so we're going to look at the dissociation of that conjugate acid of the weak base that we started with, and it's really just a Ka equilibrium problem. From that Ka equilibrium problem, you'll figure out what your H plus concentration is, which will tell you what your pH is pretty directly. And it should be less than 7 because effectively what you have in solution is just an acid. Okay, if we're after the equivalence point on a titration curve like this, then again, we'll recognize it because we've done the first step. We've determined the number of moles of acid and base. We've figured out we have excess acid here. We've used up all the base and we have extra acid. We know the amount of that strong acid that we have left over in number of moles from doing the first step. We know our total volume. We can add the two things together. From there, we can figure out what that H plus concentration is. And we get to totally skip the hydrolysis because we know any H plus that we would get from the hydrolysis is going to be super tiny compared to the H plus that we're going to get from just having excess strong acid. And so we can just take that H plus concentration and fairly directly calculate the pH from there because it's really the excess that's going to tell us what our pH is if we are past the equivalence point on a titration curve like this. Okay, just one more little quick note about indicators. Indicators are weak acids, right? And so indicators have a particular Ka value, which means they have a particular pKa value. And so most indicators are going to change color sort of right in that range, essentially. They're gonna change color based on what their Ka is. And so if we're trying to use an indicator for a particular titration curve, if we're not just using a pH meter or something, we have to choose our indicator carefully because they don't all change at the same pH. So if we use thymol blue, it goes from red to yellow and it happens between about a pH of 1.2 and 2.8. So at fairly low pHs in the acidic part of the scale. Methyl orange goes from orange to yellow, and it's a little bit higher, but still it's on the acidic part of the scale. Phenolphthalein, which we use in lab, goes from colorless to pink. It's a beautiful endpoint because it goes from being completely colorless to being really bright pink, and so you can see that endpoint really clearly, but it actually happens on a fairly basic part of the scale, so 8.3 to 10. We use it for strong acid, strong base indicators as a strong acid, strong base titration curve indicator because the titration curve is so steep right near the equivalence point, and the equivalence point happens at 7, that really maybe one more drop past the equivalence point gets you into this range where the color changes. And so we can get a pretty good change even though it's not exactly at 7. It would be a really bad idea for us to use this thymol blue, though, for a strong acid, strong base titration curve, because the color change doesn't happen anywhere near that equivalence point that we need to use. And so we really have to choose our indicators carefully. You don't want to just throw any indicator into the solution. You really want to throw an indicator into the solution that changes very near the equivalence point that you're actually trying to measure. And so you have to be a little bit careful with that as you do titrations.